All right, so we're looking at the 2.3 homework now, and I'm going to go through and talk about some of these. Like I said, I'm normally not going to talk about all of them, but I'll hit some of them and get the general idea and help you along a little bit. Some of it you're going to have to think about on your own, and there are going to be some that are going to be a little more complicated than this. There are going to be some that are going to be a little easier than this, but you've got to start thinking on different levels. All right, now find the points of discontinuity of the function and identify each type of discontinuity. Well, remember from your notes, you know that for a function to be continuous, the limit as x approaches a from the left of that function must equal the limit as x approaches a from the right for that function, and is also has to equal. Now, guys, understand we're taking one simple step past limits, because if you remember, for the definition of a limit, for a limit to exist, this is what had to happen. The only thing we're adding in right now, and let me show you this graphically. Right now, with this right here that I have written down, we know this and that. And we don't know anything about that point right there. A limit doesn't tell us anything about what's happening at a. Now, when you know that a function is continuous at a, then you know one more piece of information. You know the limit exists and the function value when x equals a is equal to that limit. So what this part right here, all it does is it takes and it fills that hole in right there. So now you know that the function is continuous, because at a, the function value is equal to the limit of the function as x approaches a from both sides. So that's the definition of continuity. Now, if they ever ask you, if you're ever asked to prove continuity, this is what you have to do. You have to prove the limit exists. If the limit doesn't exist, stop. Because if the limit doesn't exist, it can't be continuous. If the limit exists, then you prove also that the function value at a is equal to that limit. If you can prove that the limit from the left equals the limit from the right, thus the limit exists, and the limit value equals the function value at a, then you've proven that the function is continuous at a. So that's what you're looking for. Now, if we're looking for where we have points of discontinuity, what we're going to look for are problems in the domain. Problems in the domain are going to be things like where we're dividing by 0, where we're taking the square root of a negative number, things like that. So that's what we're looking for to cause problems and to give us a point of discontinuity. So with this one right here, well, I don't have any square roots in there, so the only thing that's going to that can possibly be true is, could this denominator equal 0? Well, x plus 1 quantity squared can equal 0. If we take the square root of both sides, we're going to get x plus 1 equals 0. And then we're going to subtract 1, and we're going to have a point of discontinuity at x equals negative 1. So our point of discontinuity is going to occur at x equals negative 1. So we'll go ahead and put that in, negative 1. And then it's going to ask us what type of discontinuity is going to be. Well, that you've got to think just a little bit. Is it just missing a single point, or as we get closer and closer and closer to that point, is it doing something like going to infinity, going crazy up and down, or is it a jump? We don't know. Well, you can kind of figure this out, because if we're letting this denominator go to 0, we're getting closer and closer to a 1 over 0 thing. Well, what we learned in the last two sections about 1 over 0, remember, if we're getting closer and closer to 1 over 0, that means this thing is going off to infinity, or if that's approaching from the left, it would be from negative infinity. So that means as we get closer and closer to a negative 1 value for x, this denominator is getting closer and closer to 0. Therefore, this whole thing's going off to either positive infinity or negative infinity. Which one? Well, if we're squaring it, if this is a negative and we square it, guess what? It's still going to be positive. If this is positive and we square it, it's going to be positive. So this one is actually going to go off to positive infinity as x approaches negative 1. So that is not going to be a removable discontinuity, not oscillating. Remember, oscillating is where it's going to go up and down and not settle on a single value, but it's going to go back and forth. And infinite discontinuity is when it grows without bound, and that's what's going to happen here. And evidently, my internet's a little slow here. Fantastic, though. All right, so same thing here. We're finding the point of discontinuity. For this one, we're looking for where x squared plus 3 equals 0. Well, the thing is, if we go to solve this, if we just set it up like this and solve it, we're going to move the 3 over. We're going to get x squared equals negative 3. And then we'd have to take the square root of both sides. We run into problems. We can't take the square root of a negative number. Therefore, we have no point of discontinuity. And the type of discontinuity, well, if it doesn't have a point of discontinuity, it doesn't have a point of discontinuity. All right, so the next few are going to be the same type. You just have to think about what you're doing. X squared minus x plus 3 is a polynomial. If we take away the absolute value, if we just thought about x squared plus x plus 3, remember that's going to be a polynomial. That's nice, well behaved. It's going to give us something like this, or maybe something like this. And here's the deal. If we take the absolute value, all that's going to do, if there's our x-axis, absolute value is going to do nothing more than take these parts that fall below the x-axis and flip them over. That's all it is. It's just going to make them positive. So is that going to affect the continuity? Well, that's something you're going to have to figure out. And guys, if you're having trouble with that, grab it with a graph it with a graphing calculator or something like that. But you're going to have to start making these jumps and thinking about these things analytically and figuring them out. I'm not going to work them all out for you. All right, same thing here. The points of discontinuity of the function. In this case, you got to remember you cannot take the square root of a negative number. So we're not just going to have a point of discontinuity. We're going to have a huge area where the thing is discontinuous. Anywhere, any value of x that's going to make this thing right here negative is going to cause us a problem. The way you find that is 5x plus 6 needs to be, if we're looking for where it's discontinuous, this thing being less than 0 would make that discontinuous, right? If it makes what's inside the square root negative, it makes it discontinuous. So now just solve that and then put that interval in there. All right, another one here, except for this is not a square root, this is a cube root. Still the same type of problem. Use what you know about cube roots. Now this one, guys, here's the thing. You've got to remember, these are not all that complicated. It's all just the same thing over and over, but you're applying it in a little different way. So here we're looking at e to the 5 over x. What's going to cause that problems? Well, it's going to cause that problems if this x equals 0, because we're going to have an undefined power. It still applies. You can't divide by 0 just because it's in a power. So if we can divide by, if we did this, if x equals 0, that right there is undefined. But here's what you got to do. You got to think about this. Is it just going to be that point that's going to make it undefined? Yeah, it is. So we're going to have a point of discontinuity at x equals 0. The next question, though, is what type of discontinuity is it going to be? Well, what happens is x gets closer and closer to 0. This value right here gets larger and larger and larger and goes off to infinity. If you're approaching from the left side, it's going to go off to negative infinity. So that's where we're going to run into another situation where it's going to grow without bound either in the positive or the negative direction. And if you need to see that, graph it on a calculator. Get familiar with these things. There's even graphing things online, Desmos and things like that you can use to graph these, so you start understanding what these things look like and what these things change, how they change the base graph of e to the x. All right, so this one we're looking at a graph, and you need to be able to read a graph and determine continuity, limits, whether it exists or not. So the question we're looking at here is, does f of 4 exist? Well, here's f of x, and we're looking over here at f of 4. When x equals 4, do we have a point there? Well, there's a line there, and remember the line's made up of points. These are just over-exaggerated points, so you make point, so it brings your attention to them. But at 4, there is a point there, so yes, it does exist. Does the limit as x approaches 4 of f of x exist? Well, are we approaching the exact same value from the left and from the right as we get closer and closer to 4? Yes, it is, and yes, we are. So when we put those two things together, we can look at it, and does the limit as x approaches 4 of f of x equal f of 4? Well, f of 4 is going to be 2. Approaching from this side and from this side, it's still approaching 2 on both sides, so yes, it does. So is the function continuous at x equals 4? Well, like we talked about on the very, very first slide, the very, very first question before we even started looking at the question, that is the definition of continuity. If the limit, both sides, approach the same value as x approaches some letter, some number, in this case 4, and it equals the value of the function at that value 4, then the function is continuous, so yes. All right, more along the same lines. This is only dealing with a piecewise function, but the piecewise function's graphed right here. Now, guys, don't fly through this problem. Actually, go ahead and kind of compare what you're seeing here in function notation, what you're seeing here graphically, so that you make sure that you know how to graph a piecewise function. Piecewise functions are not going to go away. You're going to see them repeatedly, so make sure you know the relationship between those and how you can graph them. You may have to sketch a piecewise function at some point. All right, determine the intervals of continuity for the following function. So where is this thing continuous? So let's look at it. It's continuous. Now, here's a special case when we have the endpoint of a function, not a point in the middle like here, but the literal endpoint of a function right there. It is continuous if the value, the point of that endpoint, and the one-sided limit that approaches it are equal. So we are continuous at 0. So at 0, we're going to need a bracket. We're going to go down here to 1, and at that point, it's continuous to 1, but it does not include 1. And then we're going to pick up 1 on the other side, and it's going to go to 2, and it's not continuous at 2. So we're going to pick up 2 after 2 again. brackets mean we're not including those, so I'm going up to 2 but not including it, and I'm going just past 2 and starting afterwards. And then from there all the way up, or all the way over to 4, this thing is continuous. Now, at this point, don't mistake it and think it's one of these. This is still only a one-sided limit. There exists a limit on the other side. There is a right-sided limit approaching 4, and it's not 0. So it's not 0, then that means that function is not continuous at 4. So we want parentheses there. And then it's going to pick up at 4, or after 4, and it's going to go down to 6, not including 4. But what about 6? Well, 6 is an endpoint. There's nothing existing over here. And the left-sided limit equals the value at 6. So you would include that side also. So looking at our options here, we got bracket 0, 1, 1, 2, 2, 4, 4, 6 bracket. Looks like it's going to be D. Excellent. All right, now when they ask you a question like this, what value should be assigned to f of 2 to make the extended function continuous at x equals 2? What they're asking is, they're saying there's not a point there. What should you assign the value to make that thing continuous? Once again, get familiar with the piecewise function. But for f of 2, to make this thing continuous, you're looking at the right-sided limit, or the left-sided limit, and the right-sided limit. What are they both approaching? Well, from this side we're approaching 2. From this side we're approaching 2. So f of 2 should equal 2. And that would make it continuous at 2. Now, is it going to make it continuous at 1? No. Or continuous at 0? Well, no, that's not possible. But they're only asking for make it continuous at x equals 2. All right, this one they're asking, is it possible to do an extended function? So in that case, you would actually have to find out, does the left and right side limit approach the same value here? If it does, then it's a removable discontinuity. Removable discontinuities, remember, you can put a single point in and fill the hole. So this one is a removable discontinuity because the left-sided limit and the right-sided limit are equal. All right, for the function below, find each point of discontinuity. Is the discontinuity removable or non-removable? Give the reason for your answer. Now, with piecewise functions, you're going to see piecewise functions a lot for continuity. And here's the reason. This is the reason why right here. They're easy to break up into parts, whereas a polynomial or things like that are not going to be as easy to see or analytically evaluate whether it's discontinuous or continuous. Right here, I can look at this and know that I have a point of discontinuity at 5. Why do I know that? Well, if you look right there, I don't have a value at 5. I have a value when x is less than 5. I have values when x is greater than 5, but I don't have a value when x equals 5. When x equals 5, y equals whatever, nothing. We don't know. So automatically I know I have a point of discontinuity at 5. Is the discontinuity removable or non-removable? That's where you've got to come in and do some math. You literally have to go in and plug in the 5 here. So that equals 2. What did I just find when I did that? I found what this part of the function is approaching as x gets closer and closer and closer to 5. So as you get closer and closer to 5 from the left side, that y value is going to approach 2. Now, from upper side, I put 5 in, I'm going to get 5 over 5 plus 1, which is going to give me 1 plus 1, which is also 2. So 5 over 5 plus 1 gives me 2 also. So that means from the right side, as I get closer and closer to an x value of 5, my function is going to have a value, approach a value of 2. So now, if both sides approach 2, remember this means the limit as x approaches 5 of f of x exists and equals 2. So now, what's the one thing that you can do to fill that thing in? Well, if you were to say f of 2, f of 5 equals 2, you could add that one point right there and you could make this thing continuous. That's what it means if it's removable or non-removable. So this is a removable discontinuity. Now, if we had plugged things in, and let's say this equals 3, there's not a single point that I can put in there that's going to close that gap. Remember, it has to approach the same value. If it does, that means the limit exists, and then all you need to prove that it's continuous is for the function value at that point to equal the same value. All right, so my point of discontinuity was at 5. Nice work. And is this discontinuity removable or non-removable? It's not removable because the one-side limits are the same. No, the one-side limits are the same, but that's not the reason why it's removable. Non-removable. Removable because defining the function at the point of discontinuity to be equal to 1 would remove discontinuity. Almost, but it wouldn't be equal to 1. It's actually the second one, equal to 2, would remove the discontinuity. Fantastic. All right, so here's another one. I'll let you guys work on it. And another one, you guys can work it. You can do it. All right, for the graph over here, find each point of discontinuity. Has a point of discontinuity at -1, at 0, and that's the end of the function. So at 0 and 1. Is the discontinuity removable or non-removable? Well, what about at -1? Well, there's not a point that's going to fill that in right there, so that one is going to be non-removable. What about at 0? Well, yeah, if we could just redefine that point right there and fill that hole in, that's a removable discontinuity. All right, so another way that you can do these as far as fixing the discontinuity is you can actually remove it by simplifying the function. Now, I'm not a big fan of the way that the computer accepts the answer because it's technically not true, but not the way that it accepts the answer as being correct. But let me show you something here. So if we pull this out over here, at x squared minus 36 over x minus 6. Now we can factor the top and we're going to get x minus 6, x plus 6. Those are going to be difference of squares. And we still have my x minus 6 on the bottom, and these are going to cancel out. So that's going to leave me with x plus 6. If you take that answer right there and you type it in right there, the computer will tell you it is correct. And for a certain point it is. There's only one problem. There is a limitation that you must keep if you're really writing this correctly. Guys, understand, you don't have to type this in for the answer, but I just want you to make sure that you understand that you have to have this disclaimer in here. And what I'm saying is that x plus 6 such that x does not equal what would make this 0. So x cannot equal 6. Remember when we talked about rational expressions, when these cancel out, we're left with a hole at x equals 6. That's why we put this part right here on there. Once again, when you put your answer in right here, you do not have to put that extended part in there, but it is actually true and fully correct for that to be included in that expression. All right, this one's going to throw some of you guys for a loop, so let me just go ahead and show you. X minus 1 over the square root of x minus 1. This is the exact same problem as the last one. You can literally take this, and that's a difference of squares also. And you're going to do the square root of x minus 1 and the square root of x plus 1. And then you can cancel stuff out. So even though that is not technically a perfect square, it technically is because you can use the square root thing. All right, so for this one, they want you to sketch a possible graph for the function f that has stated properties. You don't have to sketch a graph, you just got to find the graph that fits. So f of negative 4 exists, but the limit does not exist. All right, so here the limit doesn't exist, but the function does exist. The function has a value at negative 4, but the limit does not exist at 4. Now, that is true, and guess what you could have also done? You could have also, instead of having it come all the way down here, you could also have done that. The limit still doesn't exist, but the function still does at negative 4. Now, the problems with the other ones, what happens here? The limit exists, but it's not continuous. Here, what happens? You don't have a limit, and the function doesn't exist at negative 4. And here, the function doesn't exist at negative 4, but the limit does. So that's the differences in those. All right, find the value of for a so that the following function is continuous. Now, guys, understand, this is just approaching the exact same problem in a different way. What do we know? We know that for this thing to be continuous, the limit's got to exist, and the function has to be equal to that limit. So for the limit to exist, that means the limit as x approaches 16 from the left of f of x must equal the limit as x approaches 16 from the right of f of x. So as we're approaching from the left, that's using this function, x values that are less than 16. So we're going to find that limit by simply just plugging in 16. So we get 16 squared minus 128. And that's going to equal 128. And then over on the other side here, values greater than 16 are going to be defined by this thing right here. And we're going to let x equal 16. So we have 2 times a times 16, or we have 32a. And we want to find out what value of a is going to make this thing work. So what value of a do I need to get 32a equal 128? I'm just going to divide by 32. 32. And that's going to be a value that a equals 4. So if a equals 4, the limit exists, and on top of that, we're talking about continuity, since this one also defines it at 16, it's going to do 128 on both sides too. So the answer here is 4. Nice work. All right, another one, very similar. I'm not going to work that one out. You guys can work it out. Here, it's just finding out how much you know. I'm not going to work those out because, well, they're pretty much the same questions as we've been answering through the whole thing, except for these, you don't actually have problems with them.
this one, weak to the point, following point is not a point of discontinuity of f of x equals the square root of x minus 2. Guys, find where this thing's discontinuous. In other words, the problem children of its domain. In other words, what values of x can't be in the domain. And then find the one that's